Okay. So here we go. Graphs. This is something you can take the rest of your life. I don't care where, like what occupation you go into. Anytime you hit a graph, you can do this. Okay. So let's start with just a velocity versus time graph. Okay. So when we'll start there. The slope tells us stuff, right? So that's like rise over run. This is not new stuff. Change in y over change in x, yes? For this graph, velocity is on our y-axis, times on our x. So the slope of this is going to give us what? Acceleration. You okay with that? Let's pretend you didn't remember that. Or maybe that was an example of that. What you can do is look at your units. So this guy has units of meters per second, and this one has units of seconds. So you can do meters per second over seconds, and that gives us 1 over seconds, 1 over seconds. That gives us meters per second squared, and they're like, oh yeah, that's acceleration. Okay, you can do that with any graph. Let's say you don't know what it's supposed to give you. You can look at your units and just divide your units, y over x, and figure out if that slope tells you something important. Okay. Now, there's a whole nother side of what graphs can tell you that we've never touched. Okay. If you have velocity going for a certain amount of time, we have what's called the area under the graph. So the area between the graph and the x-axis is something. Okay, let's pretend that's 7 meters a second going for like 10 seconds. So this is going to give you, if you look at, so area is length times width, yes? Okay. So we have change in x times change in y. Right with that. So here we have, looking at our units, we have seconds times meters per second. That yields, that simplifies to meters. The area under this graph is going to give us displacement. Okay, so if I went for if I was traveling 7 meters a second for 10 seconds, I'd be traveling 70 meters. Okay, that's super easy, you don't need that. But what happens if your graph looks a little something like your velocity is not constant, like that? This trick still works. Okay, in calculus lingo, this is called the derivative, this is called the integral. Okay. Now, if we have another graph, force versus time, okay, what does the area of this graph give us? Well, this is in newtons, this is in seconds. The area is going to give us newtons times seconds. And so when we were measuring this, you'd get these spikes, yes? Okay. The area under this is going to have units of newtons times seconds. That's equal to impulse, which is also equal to change in momentum. Assuming your basketball didn't bounce, it just went from something to 0. Everybody's area under here should be identical. You okay with that? Because they have the same change in momentum. You went from moving from free fall to stop at some point. Now, if your spike, if your graph looked like this, has the same area, but you changed your momentum in a very small amount of time. What you were going for was a graph that looked like this. So I don't know if you saw anybody else's graphs, but the ones that are like look like this. The ones that sound like abrasive, like ooh, look like that. But all of them ideally would have the same area under the graph. Cool with that? So the takeaway is when you look at a graph, the slope, you can figure that out by taking the y-axis divided by the x-axis units. The area, I don't care what the graph is. Sometimes it gives you something relevant, sometimes it's junk, like it means nothing. But you can figure that out by looking at your length, your y-axis times your x-axis units. Good with that? All right. That's what I got for you today. No homework.